Okay, so the screen is visible and I'm audible to everyone. So good evening everyone. My name is Abhishek and I'm a PhD scholar at the Department of Electrical Engineering at IIT Madras. So I welcome you to the ninth live session of Multirate Digital Signal Processing, and so we'll be solving some questions that were covered in the week number 9 of the course. And before we begin, so let's recall the topics that were covered in week 9. So at first we saw the multi-rate DSP framework for multi-carrier modulation. Now this multi-carrier modulation terminology was actually used earlier as a substitute for OFDM. So OFDM was earlier known as this multi-carrier modulation. And then we looked at the M channel multi-carrier transceiver. So you remember those synthesis filters and the analysis filters, M channels, transceiver structure. And finally, we also looked at an interesting aspect, uh, namely the redundancy. So in our error correction, we know that redundancy is used to protect the information, and so how redundancy is implemented in the context of multi-rate signal processing was discussed. So we'll solve some problems which covers all these concepts. So let's get started. Okay. I believe you can see the first question on the screen. Switch to the other tab. Okay. So please read the first question. So here we are given a single carrier system with RMS delay spread of 10 microseconds. The bandwidth is given as 4 megahertz. Now it is given that the system uses QPSK modulation scheme, quadrature phase shift keying modulation scheme, with MLSE decoding, uh, so which is also known as the Viterbi algorithm. So, MLSE stands for maximum likelihood sequential estimation, and so given this information, you are asked to find the order of complexity of the decoding. So we saw right in the lectures. So the decoding complexity is of the order of m to the power L, right? Where m and L have their uh, meanings, which were discussed in the lectures. So let's let's solve this one. Okay. So at first I'll write down the given information. First thing is RMS delay spread is given. So the RMS delay spread, typically we denote it by sigma suffix tau. This is 10 microseconds. The bandwidth of the signal, let me denote it by capital B, is 4 megahertz. Okay. So now, if I have the bandwidth of the signal, I can calculate the symbol duration, right, by taking its reciprocal. And the reason for finding the symbol duration is nothing new to us, because as I already mentioned that the order of the decoding complexity is given by m to the power L, and L is nothing but your number of symbols of ISI. If you go back to your lectures, L plus 1 were the number of taps. We have a L plus 1 tap channel model, and L is the number of the ISI symbols of ISI. And in order to find L, we need the knowledge of the symbol duration, because L plus 1 is nothing but the total number of taps, which is given by the ratio of your RMS delay spread and the symbol duration. So since the bandwidth of the signal is given here, we can find the symbol duration. Okay, so I'll calculate that. So this implies the symbol duration, let me denote it by T suffix S, is nothing but 1 by bandwidth, and this is 1 by 4. Since the bandwidth is in megahertz, so the symbol duration would be in microseconds, because it's the reciprocal. Okay. And I just write down the name of this decoding. Okay, so MLSE, it stands for maximum likelihood sequential estimation. Okay, and also is also known as Viterbi algorithm. Okay, right. Now, as we know that the order of complexity of decoding is capital M to the power N. I guess there is a lag. Okay. So it's M to the power L, where what is M? M is simply the constellation size, right? The modulation scheme that we are using here is QPSK. In the question we are given that we are using QPSK modulation. See, so M is the constellation size. So in QPSK we know that the size is 4, because there are 4 symbols, right, in the 4 different quadrants. So M is 4, and L is basically the number of symbols of ISI, as I mentioned, and we need to find this L first. Okay, for that we need the knowledge of your RMS delay spread and the symbol duration. Okay, so let's write it down. So M to the power L, where M is the constellation size and L is the number of symbols of ISI. Okay. So there are L symbols of ISI, but that means that there will be L plus 1 tap channel model. Okay, so L plus 1 taps channel model. It's because, okay, there are L symbols which have been contributed by this intersymbol interference, but I also have the desired signal, right? This is desired signal. So therefore L plus 1, that plus 1 comes for the desired signal which I want to recover actually. In equalization, I basically want to eliminate the intersymbol interference. That's why I need these L plus 1 taps, and that plus 1 additional tap corresponds to my desired signal. Okay, so okay, and now since the modulation scheme is QPSK, modulation, what is the constellation size for this? Capital M is 4, because there are 4 symbols. And you can also, maybe I can draw a rough sketch of the constellation diagram for QPSK. So we have the in-phase axis and the quadrature axis, and the different symbols, let me use a different color here, are located in the 4 different quadrants, and they are all mutually orthogonal. Okay, like this. Okay, and yeah, this you can call as 0 0. This one would be 0 1. This is 1 1. This is 1 0. Again, this is the gray coding scheme, because as you jump from one symbol to an adjacent symbol, there is only a change in 1 bit. Okay, 1 bit is. So that's how the gray coding is done. So this is how the constellation looks like. So we can see that every symbol, okay, every symbol has 2 bits of information, and there are 4 symbols, right? Okay. So now we have everything required for us, and we'll find we have M is 4, and in order to find the order of complexity of decoding, we also need L. Okay, so L plus 1, which is the taps, number of taps, is equal to the RMS delay spread divided by the symbol duration. See, the situation is, here we have a RMS delay spread which is of the order of 10 microseconds, and we calculated that the symbol duration is 1/4 of a microsecond. So clearly the RMS delay spread is significantly larger than the symbol duration. So it means that in that entire delay spread, these many symbols of ISI would be captured, and accordingly I'll need these many taps. So that is equal to your L plus 1, and that is given by the ratio of the spread, total delay spread, max RMS delay spread, divided by the symbol duration, the duration of every symbol. So that captures, that will tell you the total number of such symbols of ISI. Okay, okay, great. So this is now equal to 10 microseconds is my RMS delay spread, and 1/4 microsecond is my symbol duration. So you get L plus 1 as 40, and that gives you L equals 39. So now you have M, which is 4, you also have L, which is 39, and so what is M power L? That's my order of the decoding complexity. Order of decoding complexity is M power L, which is 4 to the power 39. Pretty high complexity. Okay, So 4 to the 39, 4 to the power 39 is the answer. And if you check the options, it is matching with option A. So answer is option A. Okay, right. We have seen this in our lectures. Okay, so let's move on to the next one. So the second question. Okay, the second question is also a bit similar. We are given two systems, system A and system B, with their respective specifications. So system A has 51 tap channel. Okay, it uses 51 tap channel model, and it has a QPSK modulation scheme. Whereas system B is a 21 tap channel model with 16 QAM, quadrature amplitude modulation, 16 QAM modulation scheme. Now, given this information, and it is also mentioned that both these schemes uses the same decoding algorithm, which was used in the previous question as well. So both these schemes use the MLSE decoding, and now you have to compare these two systems and tell which of the system has the higher order of complexity. So it's again a question on the order of complexity. We have to basically do the comparison. Okay, so pretty simple. Uh, let's see. Let's see this. Okay. First, I will just write down the specification for system A. For system A, we have 51 tap channel and QPSK modulation. Okay. So we basically need to find m to the power n to find the order of the decoding complexity. Now, since there are two symbols, two systems A and B, so I'll use the notations L1 and M1 for system A, and L2 and M2 for system B. Okay. Right. So here I'll use the notation L1, which is my symbols of my side. Okay. And L1 plus 1 is actually my number of taps, which is given as 51. See, and that gives you L1 equals to 50. And what else do you need? You need M, the size of the constellation. So QPSK is given. Modulation scheme is given as QPSK, which means the size of the constellation. Let me call it M1, as I already mentioned. That is 4, because there are 4 signals. 4 signals. Right? Okay. So if this is the case, then what's the order of this decoding complexity for system A? Order of decoding complexity is M1 to the power L1, which is M1 is 4, L1 is 50. Okay, 4 to the power 50. Okay. Now, what about system B? We'll do the same thing for system B. System B, the specifications for system B is the 21 tap channel. So less number of channel taps are there, and 16 QAM. 16 QAM modulation is there. So although it has less number of channel tabs, but the constellation size here is higher because it's 16 QAM. So there are 16 symbols in contrast to the 4 symbols which are present in system A. So 16 QAM modulation. Okay. So now I'll use L2 and M2 as notation for system B. So L2 is the number of symbols of ISI, and into plus 1 is your total number of tabs, which is 21. So that gives you L2 equals to 20. And from the given constellation, 16 QAM, you can conclude that okay, M2, which is the constellation size for system B, would be 16 because 16 QAM has 16 symbols. Okay, 16 symbols. So the constellation diagram would be similar to QPSK, but here in each of the 4 quadrants there would be 4 symbols, right? Because that will constitute total of 16 symbols. Okay. Anyway, so now for this system B, what is your decoding complexity order? That is M2 to the power L2, which is 16 to the power 20. Okay, now we have to compare these two quantities. In the previous case, we got the order as 4 to the power 50, and in the second case, we got 16 to the power 20. Okay, right. So how do we compare this? Okay, so let's first match their bases. Okay, so something, the first one is 4 raised to the power something, and this one is 16 raised to the power something, but we know that 16 can be further expressed as 4 squared. So let's do that. So this 16 to the power 20 can also be written as 4 to the power 40, right? Because 16 is 4 squared. Now 4 squared whole to the power 20 is nothing but 4 to the power 40. Now, okay, well, you have clear comparison between these two orders. The first one has an order of 4 to the power 50, and the second one has an order of 4 raised to the power 40. Of course, the second system has lower order. Right? Clearly, it is visible. So, clearly, M1 to the power L1, which was the order for system A, is actually greater than the order for the system B, which is M2 to the power L2. Or in other words, system A has higher order of decoding complexity. So we are actually asked to find which one of the following systems has higher order of complexity. So we found that system A has the higher complexity. So our answer is option A, which is system A basically. Okay. System A has higher complexity. Okay. Now okay, now let's go to the third one. Okay, so this is So two statements are given here. Okay, you have to pick the right option. Okay, whether both the statements are correct, and if statement 2 is a correct explanation for the system, statement 1, and so on. Like, we have to mark the correct option. So we have to understand, for that we have to understand what the individual statements are telling us, and we have to verify whether they are individually correct or not, and then verify whether statement 2 is indeed a correct explanation for the statement 1. Okay, so let's look at the first statement. Statement 1 tells us that in a multi-carrier system, low complex equalization can be implemented. I think it will be low complex in the sense low complexity. Okay, it's talking about the complexity of the equalizer can be implemented over each subchannel. Well, that's the first statement. It's actually, it turns out to be true, because that's how we um, minimize the order of the complexity of the equalizer, right? And that's the concept that we looked into when we were discussing OFDM, right? So in OFDM, you are uh, dividing your entire bandwidth into sub channels, right? Sub carriers. So, and that actually helps in dealing with your ISI, and you can come up with a lower complexity equalizer. And so we know that this statement is true actually. And now coming to the second statement, it says that, okay, as the signal bandwidth increases, sorry, as the signal bandwidth decreases, the number of symbols of ISI also decreases. That is the claim of statement 2. And it turns out that this statement is also true, because if the signal bandwidth decreases, what it means is that the symbol duration increases, right? My bandwidth decreases, then my symbol duration would increase, because they have inverse relations. And now we know that the numbers of symbols of ISI that corresponds to your L plus 1, remember those number of taps, that is given by your RMS delay spread divided by the symbol duration. Now since bandwidth decreases, your symbol duration increases, which is sitting in the denominator. That's why the number of symbols of ISI will fall down, will decrease, right? Okay, so and that is the idea actually. That's the idea of WebGame. You divide your bandwidth into n number of sub channels, right? In order to minimize this ISI. And if the number of symbols of ISI goes down, which you know is given by L plus 1, that's the number of taps, right? So clearly the number of taps of the equalization goes down, and which results in obviously low complexity of equalizer, right? Because the complexity order is given by m to the power L, it's dependent on L. So if L goes down, then obviously the complexity also goes down for equalization. Okay, so it turns out that both the statements are individually true, and statement 2 is actually a correct explanation for the first statement, right? Because statement 2 tells that, okay, as this bandwidth decreases, symbols of ISI decreases, which actually results in the fact that my complexity of the equalizer for multi-carrier system is pretty simple. Yeah, the complexity is low if we talk about each subchannel. So that's a consequence of the statement 2. That's why statement 2 is the correct explanation, right, for statement 1. Okay, so let's put it into words. Okay. So, I've already mentioned, I've already, to tell the answer, but here I'll just briefly write it down. So before I actually write it down, let's first, clear with the notations. So here P is my signal bandwidth. Basically, I will actually use mathematical logic to prove this. That's why I'm using this notation. Ts, as we have seen, is our symbol duration. Okay, just a second. Let me put this into charging. Okay, is the connection stable? I guess, yeah. Okay. Yeah, so as I was saying, so it's the same old notation. I'll stick to the notation that I have used. L is the number of symbols of ISI. So I'm assuming everyone is familiar with the acronym ISI. It stands for inter-symbol interference. Okay, and L plus 1 is your L plus 1 is basically the taps. L plus 1 taps channel model, and sigma tau is our RMS delay spread. Okay, this is all with respect to the notation. This is the notation that we will follow, at least for this question. Okay, now let me mathematically, verify our claim. So, well, what do we know? The number of taps, yeah, basically the number of symbols of ISI plus 1, L plus 1 is your RMS delay spread divided by the symbol duration. So that is sigma tau divided by Ts. This we know. And also, how is Ts, symbol duration, related to bandwidth? It is inversely related to bandwidth. We can assume, okay, Ts is equal to 1 by B, right? Now, in statement 2, if you go back to your statement 2, what it is saying is, as the signal bandwidth decreases, number of symbols of ISI also decreases. So if your signal bandwidth decreases, which means if B goes down, then the symbol duration Ts will go up, will increase, and from this first formula, L plus 1 equals to sigma tau divided by Ts, if the denominator increases, then of course the number of taps will go down. So L plus 1 goes down, which also means like L goes down as well, right? So you can also say that, okay, the order of decoding complexity which is m power L also goes down because L is reducing. So the outcome of statement 2 is that on decreasing the bandwidth of the signal, what we are getting is number of symbols of ISI decreases. That's true, and that was actually the claim of statement 2 only, right? Statement 2 told as signal bandwidth decreases, number of symbols of ISI also decreases. So that we have verified clearly mathematically. That's true, and also that automatically implies that and number of channel taps, sorry, number of channel taps for your equalization also decreases, and hence your complexity of equalizer also reduces. You get a relatively simple equalizer. Okay. So both actually statement 2 is correct, statement 1 is also correct, and statement 1 is actually the consequence of statement 2, or in other words statement 2 is the correct explanation for statement 1. So we'll also say that okay, statement 2 is the correct explanation of statement 1, and that actually tells you that okay, option 1 is the correct answer. So here the options are actually numbered 1, 2, 3, and 4 instead of A, B, C, and D. I don't know if that's a typo or not, but let's stick to the format. So number 1, okay, number 1 option is correct. Okay, great. Now let's look at the fourth one. So all these problems are pretty simple. Okay. So fourth one, please read the question. Okay. So consider a 1000 channel multi-carrier system. So it's a we saw the general framework for the M channel transceiver, right? So there are M parallel branches, if you recall. So here that M is actually 1000. So there are 1000 channels multi-carrier system with 10 nanosecond symbol period on the channel and QPSK modulation. Good. Now if the system uses upsamplers with upsampling factor of 1024, so in the brackets it is mentioned 24 samples of redundancy. Why? Because you see originally you have a M equals to 1000 channel multi-carrier system, but you're actually employing this redundancy by introducing this upsampling factor of 1024. So this 1024 is actually greater than 1000. So if you go back to the notations that was used in the lectures, so the upsampling factor was denoted by capital N, and here this capital N is 1024, which is actually greater than your capital M, which is 1000, and the difference is N minus M, which is 1024 minus 1000, which is 24. Therefore 24 symbols of redundancy is introduced. Okay, and so this is actually the, I would say, multi-rate analog of redundancy that you encounter in error correction. In error correction, basically, At least if we talk about the classical domain, it's just the number of extra bits that you use to protect your information of the message. Sometimes we also call this as the parity bits. Okay, so that's given by the difference between the number of uh, basically the difference between the block length and the number of message bits. Okay, n minus k, that gives you the number of parity bits or the number of redundant bits. Okay, so this is the situation. So this is a problem based on redundancy. Given this information, what is the transmission throughput rate that you're asked? And again, this is also, directly from the lectures. All the questions are actually from the lectures. Okay, so let's see how can we do this. In fact, this is actually I'd recommend you to refer to lecture number 34. Okay, in lecture 34 this was discussed. Okay, in general we have M channel multi-carrier system, and in our problem this capital M is 1000. Okay, symbol duration is given as and we'll use our convention standard notation, right? TS, which is, and is given as 10 nanoseconds, and I'll just convert in SI units in seconds, because whenever we are doing the calculation it's always safe to ensure that okay, all the units are in SI. And yeah, so 10 nanoseconds is nothing but 10 into 10 to the power minus 9 seconds. Okay, because what happens is that sometimes when there is a lot of terms, there is numerator, denominator. Okay, you express some time in seconds, you express another unit in some nanoseconds, and that leads to error in calculation. So uniformity should be maintained. If you are expressing one ts in seconds, you also express the other units in seconds as well. Okay, so right. So this is a symbol duration, and it is also given that QPSK modulation is used, which means 4 symbols are there. 4 symbols, correct, are there in the constellation, and each symbol has how many bits? 2 bits, correct, because I need 2 bits of information to represent 4 symbols in binary: 0 0 0 1 1 0 and 1 1. In general, if you have m number of symbols, how many bits do you need per symbol? Log base to m, right? Log base to m, correct? So here m is 4, therefore log base to 4 gives you 2. So every symbol carries 2 bits of information. So 4 symbols with each symbol carrying, I'll use notation B for the number of bits per symbol. So B is 2. 2 bits of information is carried by every symbol, each symbol. Okay. And again, if you want to visualize the constellation, I've already drawn it before, but still, this is the in phase quadrature. Okay. Okay. This is 0 0 0 1 1 1 1 0. Okay, 2 bits per symbol. Great. Now, if you don't consider redundancy, meaning that okay, you have m equals to 1000 channel and you don't use any upsampler factor which is greater than m equals to 1000. In that case, without redundancy, so this w slash o is a abbreviation for without. So without redundancy, what is your transmission throughput rate? That is basically given by how is it given? It is basically okay. You have TS as a symbol duration. Its reciprocal gives you symbols per second, and every symbol has B number of bits. So it is B by TS bits per second. Correct? That's your transmission throughput rate. And this is the case without redundancy. So this is B by TS. Right? Okay. Let me go to the next page. Now what happens with redundancy? That's what we are interested in. With redundancy. Now if we have these upsamplers of factors 1024, that is if we have 24 redundant samples, so with the redundancy, which is given in the question, so my upsampling factor is in the lectures it was denoted by capital N, so I'll stick to that notation. That is 1024. So clearly N, which is 1024, is greater than M, which is 1000, and that means that there are N minus M, which is 1024 minus 1000, that is 24 redundant symbols or 24 samples, redundant samples. Okay, samples of redundancy. Okay. Okay, if this is crowded, let me write it again. Samples of redundancy. Okay. Now in this case, my effective throughput transmission rate would be reduced, and that factor of reduction is basically the ratio of M and N. So throughput transmission rate is M by N times B by Ts. Initially without redundancy you had B by Ts, fine. But now since you are introducing this redundancy, you have this factor of M by N sitting in front. Okay. So if you plug in the values, M is 1000 and capital N is 1024. B we found, okay, B is actually the number of bits that was captured per symbol. So every symbol of QPSK modulation has 2 bits. So B is 2, and TS we have calculated the symbol duration. I mean, not calculated, it was given as 10 nanoseconds, and we have expressed that in seconds. So I'll just substitute that 10 into 10 to the power minus 9 seconds. And if you simplify this, and by the way, the unit is bits per second, okay, bits per second. Okay. So in the previous case also, this much bits per second, okay, this much bits per second. And if you actually calculate this, it turns out to be 195.3 megabits per second. Okay, and that matches with option D, 195.3 megabits per second. So your correct answer would be option D. Fine. Okay. All right. Now let's. So hope this was clear. Okay, now let's look at the fifth question. So we are familiar with this diagram, right? This is the structure for the M-channel transceiver, right? M-channel transceiver. Transceiver meaning that there are transmitters as well as receivers. And essentially we are talking about filters here, right? We are in the domain of filter banks. We are studying multirate DSP. So on the transmitting end, we have transmitting filters, a sequence of M parallel transmitting filters, which are also known as synthesis filters, if you recall, because we are combining those individual parallel signals to produce the signal X of n, and that X of n goes through the channel C of Z, and also there is a noise component Q of n that acts on the channel, and that goes to the receiver. And on the receiver you then split the signal into different parallel components again, and using the receiving filters, which are h0 of z, h1 of z, and so on till hm minus 1 of z. And these filters are also known as your analysis filters, because that is decomposing your signal, splitting your signal into sub signals, and you're basically doing the reverse operation. On the transmitting end you did upsampling by a factor of n, so in the receiving end you do downsampling by a factor of m, and finally you get an estimate of the transmitted sequences, which is s0 hat of n, s1 hat of n, and so on till sm minus 1 hat of n. Okay, the original transmitted symbols were s0 of n, s1 of n, and so on. Okay, in the ideal case, for perfect reconstruction, we want si hat of n to be equal to si of n. Okay, right. So this is the structure for M-channel transceiver, and we are asked to find the mathematical expression for this wideband signal X of n. So X of n is the signal which is sitting right in front of the channel. You see, if you look at the figure, that's the signal, basically input signal that is passed through the channel. Okay, in fact we have seen this in the lectures as well. So in the lectures we have seen at the expression of X of n, but it was directly written down. Okay, in case you want to see the derivation of that. Maybe this will help because I'll walk you through the intermediate steps as well, how we are arriving at that uh, expression of x of n. Okay, all right. So let's solve this one, and for that I will basically redraw this diagram again. Okay. Uh, it would have been better if I would have started from the next page, but I don't want to waste this blank space here. So I'll start here itself. So this is question number 6, and the structure is, by the way, this is M channel transceiver, right? M channel transceiver. So structure, I'm basically redrawing the structure which is given in the question. So you have the first sequence S naught of n being passed through a upsampler of factor capital N. Okay, that is fed to a filter. These are your synthesis filters, right, at the transmitting end. So the first filter is F naught offset. This goes to an adder block. Okay. Okay. Right, because at the transmitter end you are basically combining the different parallel signals together. You are synthesizing all a new signal, right? That's why these filters are known as your synthesis filters. Fine. And the notation that has been used in the diagram, if you go back, so before this adder you have u naught of n. So this u naught of n is actually the output of this filter f naught of z. And what I will do is I will also use a notation for this intermediate sequence which occurs at the output of this, immediately at the output of this upsampler. Let me label that as v naught of n. Okay, I have marked that in red color. So this will be used actually in the derivation, that's why I have marked it. Okay, now similarly for the next branch we have S1 of n, again that goes through the upsampler. Then there is the filter F1 of Z. Then it goes to the adder. Okay, so this signal here would be U1 of n. It is already given in the diagram of the question, if you see U1 of n. And like I did for the first branch, I will also introduce an intermediate sequence V1 of n for the second branch as well. And similarly it continues till the mth branch. Okay, so if you continue like this, there will be a kth branch. Okay, not exactly the kth branch, but this is actually the k plus 1th branch because you are starting at the index 0. So if the subscript is k, then it corresponds to the k plus 1th branch. So you'll have some sk of n, right, that goes to your upsampler. That again goes to the filter fk of z. Okay, that goes to that adder, right? So all this dot dot dot, and again the intermediate sequence here would be vk of n, and this sequence here is uk of n, and so on. It continues till the last branch, m plus 1th branch. Okay, no, sorry, mth branch, sorry, because there are m branches. So this gives you the last signal component would be is m minus 1 of n goes to the upsampler, followed by the filter if m minus 1 of z, producing an output u m minus 1 of n that gets added. Okay, and again my intermediate sequence would be vm minus 1 of n. That's the last branch. Fine. And in the question, basically, okay, these are my transmitting filters, so I'll write it down. TX is short for transmitting filters, which are also your synthesis filters. Okay. So now these UIs are actually from the M branches. They are combined together to produce X of n. X of n. Now this X of n is actually, just a second. Now this X of n is actually transmitted through the channel. The channel is denoted by C of Z. This is your channel, C of Z. And also there is a additive noise component, okay, that acts. So the noise denoted by Q of n. So we are in the discrete time domain, that's why the index is small n, which is any integer, okay, which is a time index basically. And so this gets added, and similarly at the receiving end you will have the reverse operations. So you will again split the signal into different components. So the first filter is actually H naught of Z. These are your analysis filters, followed by downsampler, because you did upsampling on the transmitting end, so you do the reverse thing on the receiving end. That gives you an estimate of the originally transmitted sequence on the first branch, which was S naught of n. So now you get an estimate of S naught of n, which is denoted by S naught hat of n. Similarly, for the next branch, you have H1 of Z, followed by downsampler. That gives you S1 hat of n, and so on. There will be some intermediate branch, k plus 1th branch basically, which is hk of z, followed by the downsampler. This gives you sk hat of n, and finally you reach the last branch, mth branch, where you have h m minus 1 of z. Okay, this is your downsampler, and you have this. Okay. These are your receiving filters. This h naught of z, h1 of z, and so on till hm minus 1 of z. Okay, this is the structure. We need to find the expression for x of n. This is n, right? The x of n. So clearly from the diagram you can see that x of n is the sum of all these ui components, right? So u naught of n plus u1 of n plus so on till um minus 1 of n. The sum of these all m sequences give you x of n. So I can straight away write from the diagram that x of n is u naught of n plus u1 of n so on till um minus 1 of n, or I can rewrite this as x of n is summation uk of n where k runs from 0 to m minus 1, right? So I'll enclose this equation in a box because this is useful. So this, let me label this as equation 1. And if you see this, okay, we already have one mathematical expression for x of n, which is the sum of this uk's, right? So, and in fact, it clearly matches with your first option, option A. So clearly option A is the right answer. Now, since there is an option like both A and B, we need to check whether option B is also right or not. So clearly at least option A is right. So let's, okay, so the conclusion is, okay, this implies that, okay, which means option A is right at least. Now we need to check whether B is also right or not. Okay, so go to the next page. Right. And now we will be actually using those intermediate sequences that I marked in the diagram. Okay, so, and by the way, these filters, if you see the diagram, the filters are actually given in the form of polynomials of z, right? They're in the z domain. So if you take their inverse z transform, if you go back to the time index, time domain, so the usual notation is that we are using uppercase in the z domain, and that maps to lowercase notation in the time domain. That's usually what we follow. So capital F naught of z has an inverse z transform, which is small f naught of n, right? So we'll be using this. So the convention, general standard convention is um, that small fk of n has a z transform given by capital Fk of z. And here there are m branches. So this k, index k, runs from 0 to capital M minus 1. Okay, great. All right. Now let's try to explore whether x of n can be expressed in some other forms as well or not. So for that, okay, one thing we have verified is x of n is the sum of these ui's. UKs, right? K running from 0 to n minus 1. Now, since I have marked these intermediate sequences by V0, V1, and so on, we'll try to further simplify and basically actually try to express x of n in terms of vi's of n, and ultimately in terms of these input signals, input sequences, which are s naught of n, s1 of n, and so on. Okay, so let's do that. So for that, if you observe this part, this transmitter filters f naught of z. Let's look at the first branch. Let's look at the first branch, or let's look at any general branch, which is this kth branch, or the k plus 1th branch. This one, I'll mark it. I'm looking at this branch. This branch. That's why I have actually drawn this k plus 1th branch, which is actually not given in the original figure. If you see this, I've actually drawn it for the purpose of the derivation. So if you look at this branch, any general branch, k lies between 0 to m minus 1. So here, how is this vk of n and uk of n related? So basically, Vk of n goes through a filter Fk of z and produces Uk of n. Now we know that these filters Fk of z, these are all LTI systems, right? And if you pass an input to an LTI system and get an output, the output, you know, is expressed as the convolution of the input and the impulse response of the LTI system. Correct. Now we know that, okay, this filter is characterized by z transform Fk of z, capital Fk of z, and by the convention, capital Fk of z has an inverse z transform, which is small fk of n, which is the impulse response of the LTI system. And now if I perform the convolution of the input, that is Vk of n, with this impulse response, which is small fk of n, I'll get the corresponding output of that branch, which is Uk of n, right? So I can write now Uk of n is Vk of n convert with Fk of n, right? And so this is the discrete time convolution. So Uk of n, we know the formula of discrete time convolution. So we have summation Vk of, I'll use a dummy variable m, Fk of n minus m, summation m running from minus infinity to infinity, right? Okay, this is fine. This is fine. And now also go back to the diagram here. Yeah, again looking at this k plus 1th branch, which is marked, tick marked here. I'm still looking at that branch. How can you express Vk of n in terms of Sk of n? So if you see, Sk of n is passed through the upsampler of factor n to produce Vk of n. And now we know, we have actually studied that way back during the initial lectures, where we were studying about upsampler and downsampling, right? So we know if a sequence is passed through an upsampler, what output are will we get, right? We can express the output of an upsampler in terms of the input, right? So this Vk of n, if you go back to your lectures, is nothing but Sk of n by capital M if n is a multiple of capital M, and or it is 0 otherwise. That's how the output of an upsampler can be expressed, right? So I'll write it down. The reason why I am gradually going from right to left is because I want to relate my uh, x of n with the actual input, which is the S0, S1, and so on, right? So this is the step where I am actually relating Vk of n with Sk of n, okay? And then I will plug that into this formula of convolution, so that my uk of n can be expressed as a in terms of sk of n, right? So we'll see. So this now coming to the definition of upsampler. So this vk of n is sk of n by capital M. Capital M is my upsampling factor. Is of this form when n is a multiple of capital M and it is 0 otherwise. We have seen this before, we are familiar with this. And if I call this as equation 2, okay, and now if I further try to simplify this previous equation, the convolution equation that I wrote. So this one if I rewrite, basically what I'm going to do now in this equation for convolution, summation m running from minus infinity to infinity vk of m fk of m minus m, I have written down, okay, what is vk of n, what is the form of vk of n. So vk of n is some sk of n by m whenever n is a multiple of m and it is 0 otherwise. So only when the index is a multiple of capital M, vk of n survives, otherwise it is 0, right? So in this summation m running from minus infinity to infinity, if I put an additional constraint that small m is a multiple of capital M, then only basically this vk of m, the term sitting inside the summation, actually survives. Then only it is surviving. Otherwise, for all other values of small m which are non-multiples of capital M, this vk of m is clearly 0. Therefore, it won't contribute to the summation, right? So I am actually putting this additional constraint on the summation, on the index of the summation. So m, small m is the index of the summation, m running from minus infinity to infinity, and also m being a multiple of capital, right? Then I have vk of m and fk of n minus m, correct? This is my effective summation. If you consider for the terms where small m is not a multiple of capital M, then vk of m goes to 0, therefore it has no contribution to the summation. Okay, fine. Fine. So small m is a multiple of capital M. What does that mean mathematically? So let small m is some L times m. L is an integer. So we'll make this substitution here. But whenever we are making this substitution, we have to take care of the limits. So initially the index is small m. Small m was running from minus infinity to infinity. Now we are introducing another index which is L, small l, this variable. This will be our new variable. in the limits, but small l still runs from minus infinity to infinity, correct? If m runs from minus infinity to plus infinity, small l also runs from minus infinity to plus infinity, because this capital M is actually the upsampling factor, which is some positive integer in general. Okay, so this gives you, now my index is small l running from minus infinity to infinity. Vk of, I'll replace small m by small l times capital M, this times fk of n minus, again m will be replaced by l times capital M, like this, right? Now what can you say about this term? This term here, Vk of Lm. What is Vk of Lm? If you observe equation 2, that's the definition of output of a upsampler. Vk of Lm. So clearly the parameter inside the parenthesis, the time index, is a multiple of capital M. And how is Vk of n expressed whenever n is a multiple of capital M? Just look at this upper branch. It is expressed as sk of n by m, right? So this can be written as sk of Lm by m, which is sk of l, correct? Just by the definition of equation 2 I'm writing this. So this gives you summation L running from minus infinity to infinity. So I guess all this derivation will actually brush up your previous lecture concepts. So this is sk of L fk of n minus Lm, and this basically I have written it from equation 2. I have used equation 2 to write this. Okay, so this is what we are getting as a form of uk of n. So what we have got is, we have uk of n. I'm just rewriting this, summation L running from minus infinity to infinity sk of L fk of n minus Ln. Now if I call this as another new equation, let's say equation 3. Now the last step basically, okay, this is a new form of uk of n. Now how to relate uk of n with x of n, which is basically what we want. So go back to the very first equation that we looked at. First equation says, okay, x of n is simply the sum of this uk of n, right? Look at this first equation. So simply from the first equation and the third equation, we can combine these two together, or actually we will basically substitute this third equation, substituting 3 in equation 1, will get x of n, right? Will get x of n equals to summation of uk of n, right? K running from minus infinity to k running from 0 to m minus 1. This is k running from 0 to m minus 1 uk of n. Now uk of n from equation 3 is, so there will be two summation, right? This times Correct? I'll again enclose this key equation in the box, right? So this is another form of x of n that we obtain. And if you actually check the options, it is exactly matching with option B. So we actually verified that both option A and option B are correct. They are valid expressions for x of n. They are actually the correct expression for x of n. Right? So this actually tells me that option B is also correct. So both option A and option B are correct. So my answer is, sorry, I used a different ink. Okay. So my actual answer is both A and B are correct. Both A and B. It is option C. Okay. Hope this was clear, and now let's finally solve this last question. This is actually nothing to solve this question. It's a conceptual question. So the sixth question, the last question for today. And maybe what I'll do is I'll highlight some of the concepts from the lectures that you have already seen, just so that you can have a revision of those things. Okay, so in this question we are asked water filling can be performed in option A frequency domain, option B time domain, option C both A and B, that is both in frequency domain as well as in time domain, or option D none of the above. Now if you have gone through the lectures, you can straight away mark the right answer, which is both A and B, right? So option C is the right answer, because you can perform water filling over frequency as well as over time, right? So let me go to the next page. So remember the channel conditions, right? Channel conditions were changing. The SNR conditions were changing. Therefore, we adopted this strategy of water filling to allocate powers, to optimize it. Okay. Okay. So this is the sixth question. So water filling. Sorry, water filling. And we have seen water filling when we were discussing about optimal power allocation, right? In the last week, I think we have solved some numericals also. So remember that threshold line 1 over gamma naught. Okay. Based on that threshold, we basically allocate power to the individual sub-channels, right? So water filling, I'll use the abbreviation WF. Okay. What are the things we can do? Water filling we can do perform over time. That's one thing. And in that case, the channel is frequency flat. Okay, meaning that okay, it's relatively flat as a function of frequency. The varying thing is time. So it is time variant. So time varying. And the second thing is water filling over frequency. Over frequency. And that basically is the case of frequency selective channel, because my channel gain is actually not stable. Channel gain is fluctuating as the frequency is changing. Okay, so frequency selective. Okay, and let's assume for this one time is not varying, so this is time invariant. Okay, and so over time is one, over frequency is one, and the third case captures both of this, so which is over time and frequency. So maybe I'll draw a diagram and it will be more clear with the diagram. But you have already seen the diagram in the lectures. I'll just redraw it. Okay, so over time and frequency is the third case. So that's actually a frequency selective channel case as well as time varying case. Okay, I have my wireless broadband channel which is frequency selective as well as it is time variant. Okay, therefore I need to perform water filling over time and frequency. Okay, now to get a more clear understanding of this, I will just redraw one diagram which you have already seen in the lectures. You can visually actually appreciate what's going on. Okay, so I'll try to draw it accurately, okay, at least if you are able to understand. Okay, so let me this is one vertical axis, and let's say this is your horizontal axis. Okay, this vertical axis denotes, along the vertical axis we are plotting channel gain. Okay, right, you have a channel, right? The channel is characterized by some frequency response of the filter, let's say h of j omega or h of f. Okay, you are basically taking, you can think of it like, okay, the absolute value of that frequency response, mod of h of j omega or mod of h of j, h of f, whatever. So that's your channel gain. Okay, and along the horizontal axis you have frequency, frequency, frequency. You also have, this is three-dimensional figure. So along the perpendicular direction, okay, you have another axis, let's say like this. Yeah, something like this. Okay, this is my time axis. Okay, along this direction. So I have frequency axis, I have time axis, and I am observing the channel gain. Okay, great. So let's look at the case. If this point corresponds to time t equals to t naught, let's say. So now I am fixing a time instant t equals to t naught. Okay, this is time t, time t. T is the variable, let's say, and I'm actually, okay, this t doesn't look like t. This is t. Ah. So this at t equals to t naught, one instant of time, I am observing the channel gain versus frequency plot. Okay, so that, let's say, has something like this, has a characteristic like this. So let's say this, and then let's say the channel condition improves. Okay, So the second sub channel has a higher gain, right? You can see there is a increment in the channel gain. So if the channel gain is actually increased, your signal will be boosted, right? So that corresponds to improved SNR condition. So the received signal will have higher power, and the overall signal to noise ratio will be improved. And let's say the third sub channel, third interval, let's say it drops down, the channel condition becomes very poor, so it's very less, let's say the gain is very less, so it goes somewhere, drops somewhere here. Then let's say you have something intermediate like this, right? So this portion can be actually discarded, okay? Because when you do water filling, you will actually remember I told that threshold 1 by gamma naught will compare the individual SNRs with the gamma naught. If that is below the uh, threshold gamma naught, you won't allocate power to that sub channel, right? So in that sense, I'm saying that okay, we'll discard this. Okay. Now, if you have other channels like this, it's something like this. Now, so this is at a time instant t equals to t naught. What about some other time instant t equals to t1, let's say, okay, which is somewhere, it could be somewhere around here, let's say, somewhere around here. Okay, and at that time instant, so this is somewhere at t equals to t1 time instant, and at that time instant t1, I will have different characteristics. My channel will change, it will become something else. Okay, so maybe I'll use a different color for that. What should I use? Which color should I use? Let me use green maybe. Okay, so let's say you obtain something like this. Sorry. Okay, then let's say the next band it goes down somewhere here. So my water filling strategy will also tell me, okay, don't allocate any power to this sub channel because it is in a poor SNR condition. So this will also get discarded. Okay, and let's say the next, sorry, then my channel gain increases again. Then let's say somewhere here, then again let's say somewhere here, it's random, and then somewhere say here. So if you draw these parallel lines connecting these two different plots, so basically this, this, and so on. Fine. So what you are doing is, okay, the observation is that as you go from here to here, that is if you go from one time instant to another time instant, from t0 to t1, you observe that the channel is changing. The channel changes at different time instant. Okay, you have a different, altogether different channel now. The red plot and the green plot are different, right? Okay, so here, so that's the idea. That's why actually, because of this time varying thing, actually, because your channel is changing also with time, the frequency response is not flat. As a function of frequency, you have up down random, you know, it's fluctuating. So it's a frequency selective channel as well. For a given time instant, you do water filling over frequency, and then you go to another time instant at a different time instant at t1, then you repeat water filling over frequency at that time instant. So basically you are doing it in both the frequency and in time domain. Okay, so you are capturing both the effects of, you know, frequency selective channel as well as, you know, time varying channel, these two things, right? Through this diagram I think it's more uh, visible, I think. So here what you are doing, I'll write it down here. Here in this time instant t dot, you are doing water filling. So WF is short for water filling. Water filling at t equals to t naught. Okay, and at the other time instant you are repeating water filling over frequency at t equals to t1, a different time instant. So this is the figure, and some key remarks is that channel gain is varying over frequency. Of course, it is clearly, if you choose any time instant, let's say t naught, you see that the channel gain is fluctuating, it is varying as a function of frequency, which is nothing but my frequency selective channel. Its counterpart is the case when the frequency response is, or the channel response is flat. Then we call it to be a frequency flat channel. Okay, here we have frequency selective channel. And also another remark is that also the channel itself is varying over time, because we saw from this diagram that at a time instant t naught the channel has some characteristics, gain versus frequency, but at a different time instant t1 the channel changes altogether and it has a different gain versus frequency characteristics. Okay, they are shown in red and green. So these two things are happening. So what has to be done is, at a given time instant, we'll do water filling over frequency, and at a different time instant we'll repeat water filling over frequency. So both The frequency selective attribute of the channel tells me to do water filling over frequency at a given time instant. But since the channel itself is time varying, we are looking at wireless channels, broadband channels which are time varying. Therefore, we have to go to a different time instant and repeat that water filling over frequency. So both time domain and frequency domain are involved. Therefore, water filling over time and frequency are performed. So our answer is option C actually, which is both A and B. Both A and B. So it's actually, I mean, if you see the option, option A is frequency domain, option B is time domain, option C tells both A and B, which is actually the case. So option C is the correct answer. Okay, right? So, I mean, this is just a recap of the lectures actually. Maybe I'll put a note here. I'll put a note here that you can refer to lectures. Okay, it's actually the same content which is covered in the lectures, so there's nothing new. Okay, just a recap of the contents. Okay, so I think with this we have come to the end of today's discussion, and I hope you are able to understand all the problems, how we solve them step by step, and yeah, and so yeah, I should stop the recording now, and we'll meet again on next Friday, 6 p.m.